Today we talk about auroras.
An aurora, also commonly known as polar lights, northern lights, or southern lights, is a natural light display in Earth's sky, predominantly seen in high-latitude regions, around the Arctic and Antarctic. Auroras are the result of disturbances in the magnetosphere caused by the solar wind. These disturbances alter the trajectories of charged particles in the magnetospheric plasma. These particles, mainly electrons and protons, precipitate into the upper atmosphere, thermosphere, exosphere. The resulting ionization and excitation of atmospheric constituents emit light of varying color and complexity. Most of the planets in the solar system, some natural satellites, brown dwarfs, and even comets also host auroras. Most auroras occur in a band known as the auroral zone, which is typically 3 to 6 degrees wide in latitude and between 10 and 20 degrees from the geomagnetic poles at all local times, most clearly seen at night against a dark sky. A region that currently displays an aurora is called the auroral oval, a band displaced by the solar wind towards the night side of Earth. Early evidence for a geomagnetic connection comes from the statistics of auroral observations. Elias Loomis in 1860 and later Hermann Fritz together with Sophus Tromhold established that the aurora appeared mainly in the auroral zone. In northern latitudes, the effect is known as the aurora borealis or the northern lights. The southern counterpart, the aurora australis or the southern lights, has features almost identical to the aurora borealis and changes simultaneously with changes in the northern auroral zone. A geomagnetic storm causes the auroral ovals, north and south, to expand, bringing the aurora to lower latitudes. Auroras seen within the auroral oval may be directly overhead, but from farther away, they illuminate the poleward horizon as a greenish glow, or sometimes a faint red, as if the sun were rising from an unusual direction. Auroras are occasionally seen in latitudes below the auroral zone, when a geomagnetic storm temporarily enlarges the auroral oval. Large geomagnetic storms are most common during the peak of the 11-year sunspot cycle or during the 3 years after the peak. Other interesting effects occur such as pulsating aurora, black aurora, and their rarer companion, anti-black aurora, and subvisual red arcs. In addition to all these, a weak glow, often deep red, observed around the two polar cusps, the field lines separating the ones that close through Earth from those that are swept into the tail and close remotely. Auroras appear in different colors. Red. At its highest altitudes, excited atomic oxygen emits at 630 nanometers, thus the red color. Low concentration of atoms and lower sensitivity of eyes at this wavelength make this color visible only under more intense solar activity. Green. At lower altitudes, the more frequent collisions suppress the 630 nanometers mode. The 557.7 nanometers emission, which is the green color, dominates. A fairly high concentration of atomic oxygen and higher eye sensitivity in green make green auroras the most common. Blue. At yet lower altitudes, atomic oxygen is uncommon, and molecular nitrogen and ionized molecular nitrogen take over in producing visible light emission, radiating at a large number of wavelengths in both red and blue parts of the spectrum, with 428 nanometers, blue, being dominant. Ultraviolet auroras have also been seen on Mars, Jupiter and Saturn. Infrared. Infrared radiation, in wavelengths that are within the optical window, is also part of many auroras. Auroras change with time. Over the night, they begin with glows and progress towards coronas, although they may not reach them. Until about 1963, it was thought that these changes are due to the rotation of the Earth under a pattern fixed with respect to the Sun. At shorter time scales, auroras can change their appearances and intensity, sometimes so slowly as to be difficult to notice, and at other times rapidly down to the sub-second scale. A full understanding of the physical processes which lead to different types of auroras is still incomplete, but the basic cause involves the interaction of the solar wind with Earth's magnetosphere. A quiescent solar wind flowing past Earth's magnetosphere steadily interacts with it and can both inject solar wind particles directly onto the geomagnetic field lines that are open, as opposed to being closed, in the opposite hemisphere, and provide diffusion through the bow shock. It can also cause particles already trapped in the radiation belts to precipitate into the atmosphere. Once particles are lost to the atmosphere from the radiation belts, under quiet conditions, new ones replace them only slowly, and the loss cone becomes depleted. Geomagnetic disturbance from an enhanced solar wind causes distortions of the magnetotail, the so-called magnetic substorms. These substorms tend to occur after prolonged spells, on the order of hours, during which the interplanetary magnetic field has had an appreciable southward component. This leads to a higher rate of interconnection between its field lines and those of Earth. Acceleration of auroral charged particles invariably accompanies a magnetospheric disturbance that causes an aurora. This mechanism, which is believed to predominantly arise from strong electric fields along the magnetic field or wave-particle interactions, raises the velocity of a particle in the direction of the guiding magnetic field. The details of these phenomena are not fully understood. However, it is clear that the prime source of auroral particles is the solar wind feeding the magnetosphere, the reservoir containing the radiation zones and temporarily magnetically trapped particles confined by the geomagnetic field, coupled with particle acceleration processes. But that's all for today. Let us know in the comments what you think about this video and if you want to know more about this topic. Don't forget to subscribe and see you in the next video.